case anyone wants to view it later. So just make sure you hit continue. So I have your consent to record, and I'm going to turn my camera on. So if you have any questions, feel free to unmute or drop them in the chat. Both work for me. So we're going to go ahead and get started. So this workshop is covering machine learning using Scikit-Learn. And so we're not going to be covering deep learning, we're going to be covering machine learning today, and I'll explain the distinction later in the workshop. So first things first, I'm just going to load in, apologies. Let me pause share for a minute and pause the recording. Is it recording? All right, so I just loaded in some libraries that we'll use for these problems. So most of these you don't really need to worry about. I just brought in the data sets from Scikit-Learn and then imported Pandas and NumPy. So I'll explain what those do later. So we're going to be using the iris data set, which basically just holds some data about some flower species. And then the goal of our machine learning models that we're going to be building is to predict the species of the flower based on these parameters. So there are two ways to load in the iris data set. So you can load it in through sklearn datasets. So you'll have to import the datasets into your programming environment first. This method I don't recommend because basically you get things imported. You can use methods to get lists of the data, which is really nowhere near as nice. So you can use Seaborn, which is a library that's more for building statistical visualizations, but they also have some toy data sets. And so if you load it in Seaborn, this is loaded in as a Pandas data frame. And so with the data frame, it basically keeps all your everything is organized into a table of values. And so you can just index a column on the data frame to use the data in there. So it's a much more efficient way. So I'm going to be using the second method. If you want to learn more about loading in the data through Scikit-Learn, which isn't really useful, I left a link to the documentation if you just want to get some clarification on that. So first, we're just going to plot some of the data together. And so we should just have plots that relate all of our parameters to one another. And so we can tell from these plots, all the markers on the plot correspond to the species of flower that we are predicting. And so in machine learning, there are typically two types of problems. You've got regression problems and you've got classification problems. So with the difference is in a classification problem, you only have a discrete number of results. And so it's if you take a picture of a dog, a discrete problem would be whether that dog is a corgi or not. So it's either yes, it is a corgi, or no, it's not a corgi. So instead of having a continuous set of values, your values are either 0, 1, 2, or 3. Or in the case of corgi or not a corgi, you'd have 0 and 1, 1 being the positive case and 0 being the negative case. So here we can tell that the species of flower can definitely be classified based on the parameters we've selected, because there are these clean clusters for each species type. So that's an indicator that a machine learning model should work on this data set. So also just some basic terminology. We will organize our data into a feature matrix and a target array. And so a feature matrix is basically a matrix of all of your parameters. And so in this case, it's organized with examples as the rows and the parameters as the columns. So when you train a machine learning model, you train it one example at a time. And you compare the ground truth. For a training model, we use supervised learning, which means that we have a set of true values for your classifier. And so the model can strive to guess one of these values because we've confirmed that this value is true. And so basically, species is our output. And so that's known as our target array. And so when we train our model will be learning to predict outputs based on this target array and the values that are in it, because those are ground truth values. And here we have a feature matrix, which is, like I said, each example is a row and all of the columns are parameters. And so for one example, you'll have a set of values for each parameter and then one result or one classifier. So that's what we're showing with this data set. Uh, so yeah, here we're just going to basically, we're going to initialize our feature matrix. So all that I did is when you're using a pandas data frame, you can just do dot drop and then specify the column. And basically we just got rid of the species column. And so that gives us our design matrix. And then here, I just assigned our target array these species values. So we can see our design matrix is 150 by 4. So 150 examples, 4 parameters. And then our target array is 150 like rows by 1 column. And that column is just the species, or like the output of our model, basically. All right. So we're going to use logistic regression first. And so logistic regression is, well, first, like the idea behind these workshops is that I'm just giving y'all like a basis of machine learning knowledge and methods. And so we're not going to get too deep into the code or too deep into the math, but I hope that like by the end of this, you'll have a decent, just like intuitive or conceptual understanding of these methods. So logistic regression is basically a way to predict, it's a way to handle a classification problem. And so typically in a machine learning model, you have something called your hypothesis function, which is indicated by this like h theta of x here. And so we apply like a sigmoid function to our hypothesis function. And so like for a binary classification problem, this ensures that our values can only be between 0 and 1. And so a hypothesis function is what our model is outputting or predicting. So basically, if we're like I said, with like the corgi thing, like if the dog is a corgi, we should have a value in this region. If it's not a corgi, we should have a value in this region. So here we're just defining a cost function. And basically the intuition with the cost function is that the model has to have a function to grade its performance based on certain examples. And so if we have a positive example, we will punish the function. The function will have a very high cost as indicated by this graph if it's 0. But if it's equal to 1, as it should be because it only activates this function if y is equal to 1, it should have a very like low cost. And then the same applies for y equals 0. So I know this is like a bit, the math's a bit heavy, but like, I guess just to focus on the concept. So like, I think if we just go through the code and don't really do anything with the conceptual understanding, there will be like a big knowledge gap. And so I'd just rather give a brief explanation and then get into the code, but you don't really have to dig too far into the math. And so another idea is like, let's say we have 3 parameters. How do we, basically, we're trying to find the best possible parameters for a model. So you can kind of think of this as like building a function. So I guess the question is like, how do we optimize these parameters to ensure that our function will predict correct values every time? So if you feed a value into this function, we need to have our parameters perfectly tuned so the output is exactly what it needs to be. So basically, you'll take the gradient of all the parameters at a certain point. And so the gradient just gives you, and you subtract by the gradient. And so what this is doing is basically it's a way for the function to find its minimum. So it's picking a direction based on the gradient. And so if you haven't taken EA2, gradient's basically the derivative, but for vectors. And so really just think of this as taking the negative of a derivative. And so it's like looking in every direction, and it's like, what is the steepest way down? And so basically, the global minimum is where our optimal parameters are. And so what this alpha value is it's telling, okay, once we pick a direction based on the derivative, how far do we go in that direction? And so what this graph is demonstrating is how, basically with this 3D graph, what you need to envision is each axis being a parameter, or like a value for the parameters. It's trying to find the global minimum, which holds the optimal value for the parameters. So I know that's like a bit complex, and if you need me to clarify anything, like please unmute or type in the chat. But we're just going to go over how to implement logistic regression in Scikit-Learn. So it's just like 1 line of code in Scikit-Learn, so it's super easy. So the first thing you need to do is import your logistic regression model. And so all I have to do is from sklearn.model, or from linear model, import logistic regression. And now we have the model loaded into the environment. So another idea in machine learning is you train a model based on data, but you have to make sure that your model is predicting, okay, I need to rephrase this. So you have to train a model that can be used to predict data later on. And so basically in your training phase, you're going through this calculus and you're finding the optimal parameters in your model. And then in the testing phase, you're just inputting data into the model and seeing what it predicts. And so the testing phase doesn't involve any training and a lot less like computational complexity. So what we're going to get into here is we're going to split our model between training sets and test sets. And so in Scikit-Learn, that's super easy. You just from import model dot or sklearn.model selection, you just need to import the train test split. And so basically the way the order that it loads in is like x train, x test, and then y train, y test. And so x is our feature matrix. X train is our feature matrix for the training values. And then y test is our feature matrix for the testing values. And for y train and y test, they're basically our target array. And sometimes you won't have a y test target array for testing values. Like you won't be able to look at a data sample and know what the correct output should be. So you'll just be seeing what the model generates. But here we do have that. And so all we're doing here is we're applying this train test split to the feature matrix and the target array that we designed earlier. And so what this test size equals 0.2 is doing is it's saying that 20% of our data set for our feature matrix and for our target array are being split into the train and test variables. So basically our training set is 80% of our original data and our test set is going to be 20% of our original data. When we move into deep learning, it's going to be less important to have a higher value for the test size. So you can have like a test set that's like 5% or something lower, and that's acceptable. And all this random state is doing is ensuring that like the data will be shuffled when you load it in like this. And so this, I just set random state equal to 1, so it'll be shuffled the same way every time, but that's an optional parameter and you don't really, you don't necessarily need to use it. Okay, so I know I showed you the math earlier and explained the concept, but training logistic regression in Scikit-Learn is incredibly easy. So all you need to do is I set model is equal to our logistic regression class. And all we need to do is apply this model.fit method to that class. And we just need to pass our training set for X and our training set for Y. Again, where X is our feature matrix and Y is our target array. So I'm just gonna run this and it's going to train the model based on those data. So what this did is it found the best possible parameters to apply to the data to predict an output. So, okay, so one thing to note here that's pretty important and that you're going to see a lot if you work in machine learning or in deep learning is Keras, which is the next library I'll go through, and that's used for deep learning. Use model.fit to train a model, and that applies for Scikit-Learn and for Keras. So just remember, like when you use the fit method, you're passing in your training data and you are training a model. So yeah, like all of this, like the thing about coding is you don't need to like have everything like down by heart because you can just Google the documentation, but I just figured it was important to point that out. And so here we're going to use model.predict to predict values for a model. And so you have to make sure that you save this. Otherwise, like if you don't, like here I assigned it to predictions, and so we have a list of predictions. If you don't assign it to anything, it's just going to produce values that are going to get lost. So for fit, you don't have to save the model being fit. This fit will apply to the model, and the model will be trained. But for predictions, you need to make sure that you're assigning your predictions to something because that's outputting a list of values. So we just printed out the first five predictions. And so here we're just, it's spitting out a species of flower, which is correct. That's what we needed to see. So you may be wondering like, all right, we trained a model and we produced predictions for a model. How do we evaluate how the model did? So in Scikit-Learn, you can import a bunch of metrics. So a classification report will give a breakdown of precision and recall, which I will define a bit later on, so like don't worry about that. A confusion matrix, which is a really useful visualization for classification problems. It'll basically give you a matrix where each possible predicted value is the rows and the columns. And so like if it predicted a true value, it's kind of hard to explain, but I have like the visualization right here. So I will do it in tandem with that. So basically, first things first, here we evaluated a confusion matrix based on our y-test values, which are true values. So it's like the exact, it's the ground truth value. So like someone went out in the field and was like, all right, we got a flower with like this sepal length and this petal length, and we know it's of this species. So basically our y-test values are those like true representations. You know what I mean? So it's like with the corgi problem before, like it's like you looking at a picture of a dog and saying like that's a corgi and it's labeled in your data set as a corgi. What the predictions are is based on our model and based on feeding the data into our model, what was the prediction? So here again, we predicted species, and so when we run this, based on the confusion matrix, we only misclassified a single species type, which is, since we had a pretty small like data set, it's like a very solid result. So basically our confusion matrix, we have three types of flower that we're classifying. And so you can think of each type as being a row and a column. And so our first type is, let's scroll up to the data. Okay, they're like Setosa, versicolor, and virginica. I have no idea if I'm pronouncing those right. But for Setosa, that would correspond to this first row of values. And so it's saying in this first row for Setosa, how many of these did we predict were Setosa? And so here it shows that we predicted 11 were Setosa. And so that means that every Setosa that was present in our data set was correctly predicted. These would be representing the other two species of flower, so versicolor and virginica. And so if one was incorrectly classified, we would have a value in one of these columns. So I know this is like maybe a little bit confusing and hard to hear me like talk through, but if any of you would like me to clarify, again, feel free to drop a question in the chat or ask, you know. But if you have no questions, we will be moving on. So here, we're showing precision, recall, F1 score, and support. And so basically, first off, this was the confusion matrix. This is being produced from, because I printed confusion matrix first. Then we print the classification report, which is going to show us our F1 score, our precision, and recall. So right now, don't worry about what F1 score is, but as I've defined here, precision is the ratio of true positives to true positives and false negatives. So it's true positives divided by true positives plus false negatives. And so a true positive is a positive sample that was correctly predicted as being positive. Whereas a false positive is a negative sample that was incorrectly predicted as being positive. And so that's basically like, out of all the positive samples that were predicted, how many of these samples were false positives? And then, so that's what precision is. And then recall is the ratio of true positives to, true positives and false negatives. So true positives divided by true positives plus false negatives. And so those are evaluating the number of positive samples that we incorrectly classified as being negative. So since for Setosa, we correctly predicted each value, precision, recall, and F1 score are going to be 1. So that means 100% accuracy. For versicolor, precision is 1. So basically, what that means is everything that we predicted as being true was actually true. There were no negative samples that were classified as being positive. And then, what else? Yeah, recall suffered. So basically what recall is saying is we incorrectly classified virginica, which is represented in this column, as a versicolor flower. So our model misclassified one example. And then for virginica, it's saying that we had wait, false positive. Okay, so for Virginica, we didn't have any false positives because we didn't incorrectly predict any, but we did have a false negative, which ended up over here. And so overall, our model had 97% accuracy, but I guess worry less about the accuracy and just more about the number of examples that are predicted incorrectly. And so here, logistic regression worked really well, and we just had one that was predicted incorrectly. And so again, these representations are coming from confusion matrix from Scikit-Learn, this being the confusion matrix, the classification report, which is presented here, and then accuracy, which is shown here. And so you can see for like a classification problem, like a classification report and a confusion matrix are better metrics than accuracy. So next I'm going to show y'all another type of classification algorithm. And so this is support vector machines. And here we're going to get less into the math, but I'm just going to give you a bit of an intuition into what the algorithm is trying to do. Okay, so basically, if we represent data as like this is like just like a plot of data points, like a cluster plot. And so what a support vector machine is trying to do is it's trying to define a hyperplane, which is represented by this solid black line that can divide the data. And so it can say data on one side is classified as a positive example, or in the case of the flower data set, data on one side is, on this side is Setosa, and data on the other side is Virginica or versicolor. And then it's trying to find this best possible margin to place the hyperplane. And so one question is like, so we have the hyperplane oriented this way, but we could also, if this data was spread apart more, we could also have a hyperplane that was closer to blue or closer to red. But the issue with this is, let's say we're training our model on blue and red, that hyperplane could potentially be less effective because we could have, it would increase our likelihood of having a blue data point end up on the wrong side of the hyperplane. And so what it's doing is it's finding the maximum distance from each data point. And so from each data point, it's referring to a support vector. And so a support vector is basically like the closest data point. So here, blue is the support vector. All these arrows are representing the support vectors. So it's how we're reaching that data point, how far we are from it. So I'm not really going to go into the math, but like high level, like zooming out, that's what this algorithm is trying to do. And so like intuitively, you can see why that would be useful for a classification problem, because we're taking data and we're finding ways to divide them and to fit them into classes. So it'll work well for the iris data set. And also like logistic regression and linear regression aren't, like they're used pretty often, but SVM is one that's important to know because a lot of people are still using it. And so one question, if you're a pretty like astute observer, you might be like, here the data is pretty neatly clustered and it's pretty easy to find like a linear plane to put through them. But it's like, what if data is nonlinear? What if your grouping of data is nonlinear? And that's a great question. So what you can do, what support vector machines can do is they can move the data into a feature space. So here in the input space, both of these images are representing the same thing. But here in the input space, there's no way to put a hyperplane that'll classify these data points. But if you move it into a higher dimension, then you can define a plane that cuts and classifies each, all of these data points. So this is also known as like the kernel trick, but like I said, support vector machines, kind of the math behind them is I don't know that it's like more complex, but it's definitely a bit harder to understand than linear regression and logistic regression. So I'm just gonna leave that explanation at that. If you'd like to look into more, I can probably like drop a link in a chat if anyone's interested. So just drop a message. All right, so in Scikit-Learn, earlier we used linear model to import logistic regression. Here we're going to use sklearn.svm to import SVC. And so SVC in Scikit-Learn is basically our support vector classifier. And so it's going to use the support vector machine algorithm to classify our data. All right, so we have to use the test train split again to split our data into training sets and test sets. So here, again, I'm just using the pandas data frames for the iris that we used earlier. Here, I just increased the size of the test set to be 25%, and then I just set a different random state. But we'll run this, and all the data is assigned. And now we're just going to train our model. So again, all you need to do to train the model is just define a variable for the model. So here, model SVM is what I named it. You can name it whatever you want, and then just assign it to SVC. And so from there, with our SVC class, we can use model.svm.fit, and then here we can plug in our training data. And so basically just by running the cell, we trained a model already. So model SVM is now a trained model. So here we're just going to run our predictions, and Setosa, versicolor, Setosa, and Virginica. So we inputted our data correctly. Again, one thing about predictions that I forgot to point out earlier that really needs to be emphasized: when you're training, you're comparing ground truth values, which are known to be true, by examination of the data set. It's called like labeled data. So that's our Y train here. But when you predict, you're just using the data inputs, but you're not giving the model that ground truth value. So basically the model is inferring its own output based on the data. So all of its parameters are fine-tuned. And so when you input data into this model, it should spit out the right result. And so that is, that's basically the goal of machine learning, is to build these functions that can handle complex nonlinear problems and spit out a correct classifier. So here we're just going to go through our performance metrics. It basically did the same as logistic regression. We misclassified the same sample. And so also just one thing, this isn't specific to machine learning, but if you're not getting the performance you want, it can be a good idea to examine the samples that are being classified incorrectly, because they could be classified incorrectly due to your model's architecture. When we get into neural networks in a later workshop, that will make more sense, but it's important to look at data samples that are misclassified and see if you can identify a trend or something that can help you troubleshoot and inform how you adjust your model to better suit that data. So I don't know if did that make sense? This is kind of my first time explaining a lot of these things, so I'm just trying to make sure it's easy to understand if you're not already familiar with this, because I know it can be pretty complicated. So if you don't understand, it's totally not an issue. But if you do understand, you're brilliant, and that's awesome. So here, based on the confusion matrix, we only misclassified one sample. So again, with the confusion matrix, each row is one of the predictions. So our types of flowers, Setosa, versicolor, and Virginica. So here with this row of Setosa, everything that's in the Setosa row was the columns represent what we're classifying, was classified as Setosa. So again, our precision, recall, and F1 score were 100%. I'm not going to re-explain that, but if you'd like me to explain precision, recall. Okay, F1 score I didn't explain earlier. All F1 score is 2 times the precision and recall divided by precision plus recall. And so I know a lot of you are like EE, and that's basically how you handle resistors in parallel. It's the same formula. If you got 2 resistors in parallel, just multiply the values and then divide by their sum. And so here just doing 2 times that. All right. And again, we just misclassified one sample and 97% accuracy. The only reason accuracy went up is because I increased the size of the testing set. But overall, this is a pretty good demonstration that support vector machines work well for classification problems. And so next I'm just going to demonstrate some basic data preprocessing tools in Scikit-Learn, because even if you're doing a deep learning problem or building a deep learning model, you're still going to want to use the Scikit-Learn library because it holds a lot of data preprocessing tools that are pretty essential to building a good model. So I'm just going to take some housing data, and so just don't really worry about that. I just loaded in through GitHub, and I just set a pandas data frame. So in pandas, pd.read_csv will read either a CSV file, a TSV file, or a text file. And so what a CSV file is just a series of comma separated values. So I hope that's clear. Like basically in the file, all of these columns would be separated by commas between the elements in them. And a TSV file is tab separated. So they just have tabs between them. And so it's just a way to organize data. And pd.readcsv will load the data into a pandas data frame. And then using the head method on a data frame, we'll just show the first 5 rows in the data frame. And so you can see here for this housing data, we've got a lot of parameters. And so I guess the goal of this problem is these are a bunch of parameters that can be used to predict the sales price of a house. So there are classifiers for the neighborhood, house condition, area of the lot, whether the house the number of stories in the house. So I hope the year it was built. We're not really gonna like get into all of these, but maybe we can later with neural networks. All right, and now I'm just going to present like just a distribution of this data. And so to predict sales price, all we're going to feed into our linear regression model is our metric for quality, our parameter for our values for quality, living area, and the size of the garage. So here we can see that a lot of this data is into kind of like a semi-linear organization. And so the idea with linear regression is that you can pick a line through this data. And so this line is like the best predictive line for selecting values from the data, if that makes sense. And so like your algorithm will train this linear regression line. It'll tune each parameter in it. And then once you plot the line, if you add a new value to the data set, that line should be close to the new value you added. I hope that's a clear explanation. But all we're looking for when we plot this data is to see if there is like a linear representation. Because if there is a linear representation like we're seeing, then it's a decent indicator that running logistic regression will work well. All right, so now we're going to get into some data preprocessing. So here we're going to go through label encoding in Scikit-Learn and one-hot encoding. And so what I'm showing here, this knowledge is going to be most useful when you're working with neural networks. So here we're going to just take a slice of the data frame. So here we're just taking the lot configuration slice and assigning it to a new data frame, and then presenting the head of the data frame, which is just the first 5 rows. So we run it. These are just our lot configurations. And then, so basically, when you're working with a neural network, I have an image below, you'll have a set of inputs. And so the number of inputs is the number of parameters you have. So this is your input layer. And then these are hidden layers, which you don't need to worry about later. And like, don't worry about these connections between layers. I'll explain that in a later workshop. But basically, our output is the number of possible values that we can be predicting. So with the iris data, that wasn't a great explanation, but with the iris data set, it was 3 flower types, right? And so we'd have 3 output nodes if we were using that data set in a neural network. So in a neural network, well, earlier we just like left the text as it was for each flower type, and that's perfectly fine if you're using a machine learning method. But if you're using a neural network, then the network has to know which node is being activated. And so the way you can do that is you have to make a vector of the vector needs to be the same size as the number of possible outputs. So like with the flowers, we had 3 possible flower types. So it'd be a vector of size 3. And so in your examples, let's say we had Setosa and that was index 1, you'd have a vector of 1, 0, 0. And then if it was Virginica, you'd have 0, 1, 0. And so the placement of the 1 in that output vector is indicating which sample is true. So with a neural network, you have to have that vector which corresponds to each neuron here at the output, or each output node, not neuron. So you can't just keep the text as it is when you load it in from a pandas data frame. You have to, okay, so first we have to use the label encoder. So all you need to do for the label encoder is very similar to model. You just set the class equal to some variable. And so here I just have LE, that stands for label encoder, and I'm assigning the label encoder into it. And I pulled in the label encoder from Scikit-Learn preprocessing. So here, basically, we assign a new row in the pandas data frame. Don't worry too much about that code. If you want me to like explain it, just drop a message in the chat and I'll be happy to. But we'll use the fit transform method for the label encoder class. And we'll assign that fit transform to our new column in the data set. And so what the label encoder does is it takes each of these text values and it assigns some classifier like numerical value to it. So for our flowers, instead of being Setosa, Virginica, and Versicolor, it would be 0, 1, and 2. And so for our lot configurations, it defined corner as being a numerical value 0, and inside as being a numerical value 4, and FR2 as being a numerical value 2. So instead of having these text representations of our output, now we have a clear number. But again, if you're working with a neural network, that's not good enough. You have to have a vector where the one value in the vector is corresponding to each of your output nodes. And so based on how a neural network predicts outputs, that'll be more obvious. And again, in the next workshop, we'll go over neural networks. So all will be like clear then. But since this is the workshop of Scikit-Learning, I wanted to introduce all of you to label encoding and to one-hot encoding. So here, all I did was load in the one-hot encoder, and then I initialized, like I said, with all these like classes in Scikit-Learn, all you've got to do is pick a variable and initialize that class to it. And then we're making a new data frame for our one-hot encodings. And so all we're doing is, basically this pd.data frame, I'm just like typecasting this to a data frame. And so we're using the fit transform function on these lot encoded values. So you can't go text to one-hot encoding. You have to go text to label encoder to one-hot encoding. So we're using this on our label encoded values, and then we're setting them to our one-hot encoded values. And so if my explanation of one-hot encoding wasn't clear earlier, since our label encoder said numerical value 4, the fourth column in our vector for one-hot encoding has the value 1. So that's saying this is the fourth type of prediction. Does that make sense? I hope I'm explaining this clearly. And so just the placement of the 1 is corresponding to what type of output it is. Again, like if you're like I keep bringing this back up, but if you're taking a picture of a dog and you want your algorithm to predict whether the dog is a corgi or not, it would have just 2 columns, and one column being a 1 would represent that the dog is a corgi, and the other column being a 1 would represent that the dog is not a corgi. So you can only have one placement of the number 1 in the vector. And again, that's to match the number of output nodes for the neural network. And so in order to train a neural network, you have to pass in your ground truth values as these one-hot encoded vectors. So now we're going to go over multivariable linear regression. And since I'm running out of time, we're going to do that very quickly. So basically with linear regression, like I explained before, we're predicting a line that's going through the data. And so that's our hypothesis function. And so this is just this is y equals mx plus b. This is the intercept, and then this is the slope. And so we're finding the best possible slope for each parameters. And then earlier, like here, all this cost function is saying is it's comparing our predicted values against the true values, and then we're minimizing that difference to find the best possible parameters. So again, here, basically all this is showing is that this is a convex function, and so it only has one global minimum. And so that single global minimum is the best possible values of our parameters that we can use to make a prediction using machine learning. So we'll probably start somewhere up here, and then using gradient descent, we'll just hop down and then find our way to the global minimum. So again, like in order to use these algorithms, you don't have to have a super solid theoretical understanding, but I think it's good to just have a base. So all I'm doing here is initializing my feature matrix and my target array. So our feature matrix is defined based on the data of the 3 parameters we're testing. And then our target array is just the slice of the data frame that has the values we're trying to predict. So we're trying to predict sales price based on quality, living area, and the number of cars for that house. Okay, so here again, to make a model, all we're doing for preparing a linear regression model is from Scikit-Learn linear model, import linear regression, and we're setting the linear regression class equal to some variable. And then we're using the fit method to pass in our X and Y values to let the model learn and come up with the best possible line for linear regression. And so what I'm showing here in this cell is the intercept of the linear regression model and the parameter values. So we had 3 parameters, and so that means when we make this line, it'll basically, instead of having like one term here, it'll have 1, 2, and 3, and then the intercept, right? So this is our intercept value, and then these are the values that were best for each parameter. And so like I showed earlier, what this linear regression is doing is it's picking the best possible line through the data with which to predict an output. And so like we have this data cluster here, and let's say we add a data point. This line is basically the most likely point for that data point to be. And so it's the best way to predict the output of the model. And so that's all I'm covering today. I know that was a lot. If you'd like to ask me any questions, please let me know. I'm going to stop recording.